I'm Venkatesan Guruswami. I'm a senior scientist here at the Simons Institute for the Theory of Computing, and also currently its acting interim director. With me today is Nikhil Srivastava, who has just joined us this summer as our newest senior scientist. Welcome, Nikhil.
Oh, hi, Venkat. Yeah.
Hi. So how did you first get interested in theoretical computer science?
Well, let's see. There were a couple of events like during undergrad. In the beginning, I was mainly interested in math, and also I was doing research in non-theoretical computer science, namely like databases. And so in this database research, I somehow I went with my advisor to VLDB 1 year.
And where was your undergrad?
It was at Union College in upstate New York. Okay. Which is like a small liberal arts college with like 2,000 people in Schenectady. And so I went to VLDB, and I remember going through all the talks, and one talk really jumped out at me, and it was a talk about using graph algorithms to optimize queries, like probably something that's being studied, of the type that's being studied in the program here. And I just didn't know that there was this thing where you could do math in this computer science context. So that was one important event. And then I guess another one was, it was really influenced by the people who mentored me. Like my math advisor somehow recognized that maybe this is something I would like. And so he showed me some problem, which was some simple algorithms problem. And that was like the first thing I proved that wasn't known before. And that just felt incredible. So
that's great.
Yeah, it was really influenced by these two advisors that I had. And then, well, finally, I didn't make up my mind. I applied to half grad schools in theoretical computer science and half in set theory, which was the other thing I was interested in. And then I actually couldn't make up my mind, even on April 15th or whatever. I just couldn't make up my mind, so I asked for an extension. And then some unnamed faculty member at unnamed university told me that, listen, if you do set theory, there's no way you're going to get a job. So I was like, okay.
Nice path, and it's great to have you among the theorists. And what research questions are you interested in these days?
So I spent the last couple of years thinking a lot about questions in linear algebra. So, it kind of goes back to a conversation I had in 2018 with Peter Bergesser, who told me, he's like, listen, like there's this problem, like, given a matrix, diagonalize the matrix, like compute its eigenvalues and eigenvectors. And this is something we all learn in undergrad. And okay, for those who don't know, eigenvalues and eigenvectors are a mathematical concept that corresponds to computing, let's say, resonant frequencies and resonant modes of physical objects. So this is something that felt like this should be just totally understood, like, to the level of sorting or something, where we have algorithms, we have proofs that they always work, and somehow this should be something that's very understood. But he was like, actually, the best known algorithm for this problem is like n to the 10.
Wow.
And so this was like really striking to me. And so I was like, well, how can that be? Like, how is that possible? So then I really got into this area of trying to find provably fast algorithms for diagonalizing a matrix. And this worked on this for a few years and eventually made quite a bit of progress. We're still not at the level where it's as well understood as sorting, but it's it's comparable to the time for multiplying matrices. So that was what I've been doing in the last couple of years, and that kind of brought in. The reason that it brought in ideas from math, like random matrix theory, and that kind of explains why it probably wasn't known 50 years ago or something. But yeah, I don't know, I'm kind of at an inflection point right now. I'm really influenced by some things I've seen at the Simons Institute. I found, for example, the quantum program this summer very exciting. And I've been kind of a quantum groupie for many years. I've been kind of just watching and like reading papers and haven't done anything yet. And
quantum is linear algebra on steroids, right?
So I think it's about time. And I think I'm probably going to start working on quantum Markov chains.
Oh, excellent. And speaking of your connections with the Simons Institute, you were a research fellow in the first semester of programming at Simons Institute in the big data program, if I recall right. Yeah. And I think you've been a participant in numerous programs since, maybe over 10, in fact.
That's the official...
to varying degrees, I'm sure, but still it's a really impressive number. Shows your, I guess, wide-ranging interests and also how Simons Institute connects with your research. So what makes the Simons Institute such an important venue for theory of computing, and how do you see the institute having evolved during the years you've been part of it?
The most obvious change to me is, in the beginning, when it was new, when visitors came in, it would be their first time, and it was kind of this new, exciting thing that was happening. And now it just feels like people are coming home or something. Like, because everybody, many people who've come here have been here before. It feels kind of very cozy. It's a lot louder, which is really nice. Like it just feels more like coming back home than to some new place where you have to be somewhat formal. I mean, that's the most obvious difference to me. In terms of the programming, obviously, there's been a shift. There's an increasing emphasis on certain research areas, notably machine learning and quantum. I guess the community has, or the core topics of theoretical computer science have grown in this time period, and that is one of the goals of the Simons Institute, which is to really engage with adjacent communities by inviting people from those communities over, and really it does take a whole semester to create that kind of engagement, and I can really see that that's actually happened now. The community has actually grown as a result of the programs that we've had here.
Yeah, and certainly a lot of youngsters routinely come through, so it influences them through their career too. It's not just established.
Yeah, that's one of the nice things, right? I guess there's a big effort in all of the programs to make sure that a large fraction of the people are postdocs, because they're the ones who are going to. Have you noticed any major changes?
Yeah, I guess, some of it is, when I came as a visitor, one thing I've noticed, it's different being here on a permanent basis than just coming here for 4 weeks or something. But I guess, I've also noticed that there's a lot of increasing energy, a lot of visitings, not just postdocs, but visiting students. And some of them have explicitly told me that sort of, even if they have a relatively good sized group in their home institution, being immersed like this in their area for 4 months, that is an experience they're very privileged to have, and they realize that, and you can't replicate that anywhere, however big a theory group your institution might have. So I think, and then this really informs them, and especially for programs with straddle theory and practice, they kind of come away from it with a perspective which really sort of is far beyond what you would expect somebody with a PhD student to have, and that can really have lots of impact going forward, right? Because it can really inform their research and stuff. So I'm kind of really excited to see the next generation, and we have already seen that in our 10th anniversary thing. Some fellows who came through this sort of really thank the institute for sort of informing this aspect of their research. I think that's going to continue, so it's great.
I think it really speeds up the process of entering a new research area, right? Like, no matter how big your theory group or whatever is, you can't have everybody there.
And even if you are working in an area, it might say, oh, there is this is why it's really important. Oh, there are all these other people also interested in it. Now I'm really excited. There's that also. Sometimes, research, especially in theoretical areas, can be a bit isolating. Like you and your problem, and you're like, okay. But if you see a greater ecosystem in action every day, that can be really sort of energizing. I guess,
and simply the type of information you get is different, right?
That's different.
If you get to talk to everybody in the field, that's kind of the only way you can gauge the difficulty of a problem, because you can know, well, what do people not know? What have people tried, etc. And you just can't find that written.
Yeah, exactly. I think there's a lot of things which, exactly as you say, you can't pick up from just papers and surveys, and it's really sort of, I think being in this atmosphere, people gain that. That's great. So. And also, speaking of adjacent areas, you are, I guess, officially a mathematician, but your interests clearly fit the kind of research that happens at the institute, just judging by the number of programs you have participated in. But for those in our audience who may not be so familiar with intersections between math and TCS, can you explain about that? And perhaps, do you bring, and you kind of mentioned this a little bit in your linear algebra part, do you bring a somewhat organometrics part? Do you bring a special mathy flavor to your work, and how do you see that going forward? So
So let's see. So Well, yeah, okay. So I'm the same as everybody else. I'm a theoretical computer scientist, but I am in the math department, so I have seen how it works in math, and it is a little different. So, I mean, first of all, math is just huge. Like, it's really much, much, much bigger than theoretical computer science, and so maybe the the important feature is that the culture in different subfields of math is very different. Also, that like how are like who decides what are the important problems, for example, or how fast like what is the typical rate of publication? Are people in some areas like combinatorics, it's very common to write lots of small papers on problems, whereas in other areas it's more common. It's expected that you will spend a couple of years and write a paper that's like some kind of a large tome. Different fields are also, I mean, some fields are really outward looking and others are not. Others are basically following the agenda set by some small group of people. And so, I mean, that said, an overall difference between theoretical computer science and math is that in math generally, at least in pure math, the goal is just, I think, mainly aesthetics. Like it's purely aesthetically driven. People want to find proofs that are kind of beautiful and deep and uncover some interesting mathematical structure. Whereas in theoretical computer science, we have two goals. We have this kind of mathematical depth goal, but we also are motivated by computer science. So we have this goal of being practically relevant, or of producing algorithms that are efficient, which is actually a different goal from. I mean, on the face of it, a different goal from just the goal of mathematical depth. Yeah. So sometimes these things align beautifully, and that's kind of the nice thing about theoretical computer science, that you when you're looking for these nice algorithms, you find some new, interesting math, and sometimes they don't align, and that's that's one of the hazards of working in this field. Yeah. I mean, that's pure math. Applied math is much closer to practice, I would say, than theoretical computer science. And one of the things I hope to maybe increase during my time here is interaction with applied math. So strangely, TCS has not had that much interaction with applied math. I don't know, in your field, is it different?
Yeah, so applied math, I guess if you take things like combinatorics, there has at least been a lot of back and forth, between some areas of TCS, like pseudo-randomness, notably, and combinatorics. But I guess, if you mean more of the sort of computational things like fluid dynamics, numerical analysis, and so on, I guess there is definitely a lot more potential for interactions. Probably that's what you're referring to.
Yeah, I mean, I'm viewing combinatorics as pure math.
Okay. So,
I mean, like, people who actually compute things.
Okay. Yeah. I think there's some element, of that, right? And it's also interesting you mentioned that some parts of applied math are actually closer to practice than theoretical CS tends to be, because we have a bigger road from algorithm development to deployment, whereas they kind of probably develop things kind of motivated by a concrete engineering or scientific simulation need, and so the research is more closely informed by that. So
that is my sense, and that was one thing I was surprised to learn when I learned more about applied math, that they actually don't even necessarily care as much about proofs as we do. That they really care about the application. And so the scientific culture is very different. They're not as like we still have a very pure math culture. We're driven by like big open problems, basically. And so
and I see a little bit of that in sort of my research area in error correcting codes. I mean, it's done by multiple communities, one of which is electrical engineering, information theorists, and also by computer scientists. And there's a little bit of, I think they tend to be they really care about their solutions being sort of more importable to practice than, say, a computer science perspective would be, where we want that clean theorem with no bells and whistles, everything proved and stuff, right? And whereas if it's 90% proved, whatever it means, but if it's going to change the way you store or communicate data, I think that's great, because somehow it has a little bit stronger ties to an engineering viewpoint than computer science, which maybe kind of came a little bit from math, logic, and science and so on. But I think that the gap is bridging, and that's one of the exciting thing. And people at least understand each other's language and sensibilities, and so that's already progress.
And that's one of the things the institute has been really good at doing.
Yeah, exactly. Yeah, and in fact, we had a program which brought together, both sides of the aisle on coding theory about 8 years ago. We'll do it again next year. So yeah, exactly. The institute is good at that. Yeah, I think, thanks a lot. I think that's very informative. I'm glad
I wanted to ask you some questions too. I mean,
okay, sure.
I mean, this is kind of a semi-new role for you too, like 1.5 years ago.
Yeah.
Or something. So I mean, so you're taking Shafi's place right now as director.
Just for the semester.
Just for the semester, yeah. I mean, how has that been? Do you have any ideas about what you're gonna do this semester?
I mean, in some sense, I mean, the institute is in a great place. I mean, Shafi is an incredible director. Her passion and dedication to the institute is amazing. She's constantly creatively thinking about how to make the Simons Institute fulfill its mission even better, so that really for the greater good of theory worldwide, right, and theoreticians. So I think, in some sense, all the higher level pieces are really in good shape. And in terms of day-to-day thing, the Simons Institute is, in fact, a really well-run place, right? I mean, the programming is very well-oiled, and the staff are amazing. Everything, the associate director Sandy Irani, she's really on top of programming, planning for all the programs and the workshops and the outreach lectures and so on. So everything is going. So there's maybe one of the things I'm sort of thinking about is, we've had an extremely busy past 2 years. Some of it is just coming back from sort of COVID, and people were raring to go, and we had lots of exciting proposals. So the institute has been kind of running non-stop, literally, for 2+ years.
Yeah, after COVID, there was this tremendous energy.
Yeah. So I'm sort of helping planning the programming for the next year or two, and we might sort of take a little bit of breather and sort of see, have maybe kind of go back to normal older times when it was not maybe as hectic. And some of it is also dictated by external considerations of fundraising and logistical things of space and staffing availability and so on. So that's something we are planning. And on the other hand, we get great proposals. So somehow trying to understand how to plan for this is something I'm thinking about. And also helping Shafi. I mean, Shafi, I should also say, I mean, she's still very much engaged in the higher level aspects of planning ahead for the institute, like fundraising and stuff. So
it's quite remarkable that on sabbatical.
Yeah, exactly. So it's not. So I'm trying to assist her in some of those aspects as well. Trying to both because we have a very generous match offer on the table from the Simons Foundation, for which we need to sort of do philanthropic fundraising. So. But I'm also interested in, our programs are also on the cutting edge, and I feel like any federal agency should really be supporting many of these activities. So I'm trying to also find out options to do some fundraising in those aspects as well. And the other thing is that as senior scientist, I was a little bit more insulated. Maybe I was focusing more on the fellows program, some of the scientific aspects, but and I knew some subset of the staff very well, but maybe not the entire crew. So I'm also hoping to use this as an opportunity to get to know the operation staff who day in and day out keep the place running like clockwork.
Yeah, it's amazing how well run this institute is.
So I'm trying to get to know them better and maybe understand also what are some of the pressure points and how we can make ease things for them, and that also will in turn help the institute run in the same way for the next decade, right? So.
Sounds like a real job.
It is. I mean, I would say so. Yeah. So, but it's great. Yeah. Shafi deserves this little breather from the nuts and bolts, and I think it's a good way for me to learn some aspects of the institute which I didn't maybe appreciate that much before. So.
And has being here, how has it affected you scientifically? Has it affected your research agenda or how you choose problems?
I mean, yes and no. I guess no in the sense that I tend to be, maybe I'm still a bit old school, so I'm sort of still working on some classic themes of the field, maybe trying to slowly push the frontiers of it, or maybe work on some new themes or maybe newly hopeful themes because of some recent developments. But still, it's sort of old problems. For example, one problem, various variants of which always continue to excite me, is constraint satisfaction problems, which are of course the bread and butter of TCS. They've been behind NP completeness, PCP theorem, unique games, a lot of semi-definite programming algorithms, and so on.
It's amazing how it falls in this abstraction.
Yeah, it's sort of this sweet spot between generality and structure. So as a result, it's a really great test bed for like both algorithmic and complexity theoretic techniques. And here there was this major development of the dichotomy theorem, which gave a precise link between, which problems are easy and which are hard, and why are they easy, and not just that, but also why are they easy, and why are they hard.
So is there a one sentence explanation of why?
So, I mean, if I have to say it at a high level, in some sense, if your solution space offers some higher order symmetries, then you can somehow turn that into an algorithm. You can sort of think of it as some sort of a discrete convexity. So a lot of problems in continuous optimization are easy because of convexity. So there is an analogous notion you can capture here using something called polymorphisms, essentially homomorphisms from higher powers. And that somehow seems to hold the key, and it's very precise. And that's amazing, as a scientist, this is what you sort of, you want to understand nature, you want to understand why something is the way it is. And this explains it for efficient algorithms, which is a very complex phenomena, but of course only for the stylized world of constraint satisfaction problems. So one of the things which would be great is to sort of be emboldened by this and push this further beyond constraint satisfaction. And I'm working on some models and on that. One of the prominent ones is something called promise constraint satisfaction. It's probably a bit technical to define in this scope, but I would say a prototypical problem is like approximate graph coloring. I can give you a graph, tell you it's 3 colorable, but I can ask you, hey, can you at least color it with 10 colors, right? So this is a problem we currently don't know the complexity of. And
so that's the promise that you tell me.
Yeah, the promise. I give you a stronger guarantee. I hold you to a weaker requirement. So that's something I work on. I've also been, you mentioned various things about linear algebra. So one of the things I've been involved in recently is algorithms for the semi-random instances of constraint satisfaction problem, where a lot of spectral techniques have led to some nice algorithms. And this also has led to some interesting applications in coding theory, which is the other main hat I wear. So where we used some of these CSP algorithms as a way to prove some lower bounds on certain kinds of error correcting codes called locally decodable codes. So that was sort of very nice when these
so there's this interplay between the spectral world and this discrete.
Yeah, you can sort of think of a code as a collection of constraints, and you can then prove non-existence of a code by basically saying that that collection of constraints cannot have a satisfying assignment. And you can take that connection, and it actually leads to the state-of-the-art results in one model, which is nice.
Yeah, actually, one of my favorite, when I was a grad student, one of the first papers I read was your paper on Euclidean sections of L1. Which was this incredible kind of blend of coding theory and continuous, like high-dimensional geometry insights.
Yeah, there are some things related to that also we recently worked on, but again, there are many things we don't know there. For example, if you throw sparsity into the mix, we don't know what exactly happens. So in coding theory, I'm also excited by, I think as a field, it's very interesting because you get some very deep mathematical questions, but we somehow naturally arise from some modern technological reasons. For example, distributed or cloud storage led to a host of new demands on what the code should offer. And that leads to often some very deep questions. And it's also very practically relevant, saving lots of, huge amounts of money for cloud providers.
Yeah, my understanding it's actually been implemented.
Yeah, many of these things are implemented, and the math is very, very nice. For example, recently we had some work using non-commutative polynomials, which give some state-of-the-art codes, which probably are deployable and or maybe already deployed. I don't know. So that aspect of coding theory is, in fact, really interesting.
So it's a field where you can actually have the sweet spot of having mathematical depth and
I tend to work on the very mathematical end of the spectrum, but there is a spectrum, and sometimes you get really beautiful math questions which have impact all the way. And polar coding is another example, which is in 5G standards, but asks beautiful questions about martingales and probabilistic phenomena.
Yeah, that was really stunning.
Yeah, and so all this is continuing on in terms of being influenced by being here. One thing how to pick problems. Basically, I try to push on some of these directions in reacting to what's happening in the community, but also revisiting old questions when I have some inspiration. But some of being here, I think I'm really sort of excited by quantum error correction now, thanks to all the activity here and working on it as well. And I'm quite excited because it's really a new facet, and there have been really amazing breakthroughs in the field, so it seems like a good time to, at least one should know about these things. And
huge breakthroughs.
Yeah, and there are some interesting things we're working on, and some of it is really influenced by students. I mean, I think I've said this before in other sort of my Q&A when I started here. One of the points I made is the field is incredibly lucky for the amazing talent it attracts, right, in terms of the students we get in year after year. So I'm blessed to work with, amazing students, and some of the research is directly informed by what they want to work on. So quantum is one example. I'm also interested in parameterized complexity these days because of collaborations with the student. And also on some questions, it's sort of at the intersection of coding meets communication complexity meets streaming. There are some surprisingly interesting questions in that nexus which haven't been explored, and some sort of thinking about some of these things. And these are really, things which have happened for me because of being here and at Berkeley, not just the institute, but also the Berkeley Theory Group. So
yeah, same. I mean, this interest in quantum is somehow largely because I have like half my students that that's what they want to do. So.
Right. Yeah. And they have a great opportunity here to get a wide perspective on quantum.
Yeah.
And, they teach me. So So I think it's exciting. Yeah. Of course, busy to juggle all this with other hats as well.
I don't know how you do it because I keep seeing your name as being, the editor of the such and such journal and like moderating the archive. And I'm like, I don't know how Venkat does all this.
Well, have good collaborators and good colleagues. And I guess that really helps. Yeah. Well, thanks, Nikhil.
Thank you.
And this has been a lot of fun. And thanks to all of you in our audience. And please don't forget to like and subscribe. And we hope to see you in Berkeley and at the Simons Institute soon. Thank you.